This video introduces the method for finding the area of polar curves. Now, for each one, it is a good idea to follow the 3 steps involving sketching the graph, so you know which area you're focusing on. Then you need to establish the limits. Sometimes they will be given to you in the question. Sometimes you just use between 0 and 2 pi, but as we will see when we do example 1, we sometimes need to do a little bit more work to establish the limits we are going to work with. And then you integrate. The area of a polar curve is given by this formula here, which is on page 17 of your formula book. You will often need to know your double angle formulae. These are the rearranged versions that you met in your A2 maths, rearranged so that we have cos theta, or alternatively sine theta. Notice I've given you one example with revise the double angles, but it's always the cos double angle when we're dealing with sine squared or cos squared. Right, let's have a look at question 1. So you can see that I've got my sketch ready. And we are dealing with this equation here. By looking at the equation, I know that I've got a rose with 2 petals. Obviously, you will check on your calculator. Now for this, you'll also be aware that there are some hidden petals where R is negative, which we do not include in the sketch. However, we have to be aware of that when we are establishing the limits we're going to work with. If I just apply the formula for the area to R equals sine 2 theta, I will get the area for the petals when R is positive, but it will also include the area when R is negative and therefore give me a wrong answer. So what I need to do, and the method I'm going to use for this question, is I'm actually just going to find the area of one petal and then I'm going to double my answer. But I need to know the angle that is involved when the curve moves from the pole out round the petal and then back to the pole. So what I do for this is I'm going to set R equal to 0, because at the pole R is equal to 0. So I'm establishing my limits. I do that by letting R equal 0. So that means that 0 equals sine of 2 theta. This is a standard trig solve. So for 2 theta, I am going to get 0. And then because it's sine, I'm going to be doing pi minus my principal value. And then I'm going to add on, or take off 2 pi. In this case, we're going to add on because we're going in the positive direction around the poles. So I also will have values of 2 pi, 3 pi, and 4 pi. I need the values for theta, so that's going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. And I know that 2 pi and the 0 will be equivalent. So now let's have a think. 0 is when we start off at the pole and start to go around the petal. Pi over 2 is when we return to the pole. The pi and the 3 pi over 2 will give me the second petal over here, and then I'm back at the beginning again. So I'm going to find the area between 0 and pi over 2. we'll call it A1. So we'll say A1 equals a half of the integral between 0 and pi over 2 of r squared. So r squared 2 theta d theta. And you will now see what we've suddenly got to think about integrating sine squared, because I've squared my equation here, and often polar equations involve sine of theta. So I'm going to replace sine squared 2 theta with the double angle formulae. And I've already written that out at the top of the page. Okay, so let's work through that. I have a half. I also have a half in my formula, so that's going to give me another half to bring outside the integral sign, 0 and pi over 2. And I've got 1 minus the cos of, and it's 4 theta because I have 2 theta in my question. Simplifying and integrating, we get a quarter theta minus a quarter sine 4 theta, pi over 2 and 0. Subbing in and evaluating, I will get pi over 2 minus a quarter sine of 2 pi. And then when I sub 0 in, I'm going to get 0. So that gives me an answer of pi over 8. That was one petal. I need the area enclosed by the curve, so that means I need to double this answer because I have 2 petals, so my area is pi over 4. So I've sketched my curve, I've established my limits, and I've performed the integration using the formula. Interestingly, if you did this integration and we did it between 0 and 2 pi, so we went all the way around, you would get an answer twice the size of that. So that's introducing the formula for the area of a polar curve in a situation where we're dealing with a rose. Now let's have a look at question 2. Give you another example. Again, I've used my calculator to help me sketch the curve, which I have here. As you can see, I'm looking for this shaded area here. Now, in this case, they're asking me to find the area between 0 and pi over 3. So if I think about the curve, I know that there aren't any negative parts. I know that it's a circle, symmetrical about the initial line. So if I were doing the whole of the circle, I would just integrate between 0 and 2 pi, but it's been restricted to be between 0 and pi over 3. So I'm just going to integrate between 0 and pi over 3. I don't need to set r equal to 0 in this case, as I did in the previous question. So my area for this one will be a half, and it's r squared, so that's going to be 16 cos squared theta d theta, and I'm going to be using 0 and pi over 3. Really important that I have them in the order that I need to get the correct area. And I appreciate for this, they are in numerical order. If I swapped these round, unlike previously when I was integrating, it won't give me the negative, it will give me the area from pi over 3 round to 0. So it would actually give me the parts of the circle that are not shaded. So you need to be thinking about sectors and moving through the angles when you're establishing your limits. Okay, now I need to do the integration. So again, it's a cos squared, so I'm using my double angle formulae. Simplifying, bringing the constants out the front, I will get 4 at the front and cos 2 theta plus 1 d theta. So that's a 16.5 from my double angle formulae. That gives me the 4. I then integrate and evaluate. So 1/2 sine 2 theta plus theta, 0 and pi over 3. You can, of course, put this on your calculator. But to evaluate, we'll get 4.5 sine 2 pi over 3 minus, plus pi over 3 minus the 0 subdim, which again gives us 0. And that gives me a simplified answer of √3 plus 4 pi over 3. And you will always leave in exact form.